Hello. I'd like to talk to you about a new method of treating textiles. It's one that is incredibly, unbelievably environmentally friendly. I think it's probably the biggest development in our sector for generations. It's a new technology called MLSC. Now, those of you that aren't familiar with Huddersfield may not know that we haven't always had the best reputation for taking new technology to our hearts and embracing it. In fact, 200 years ago, textiles around here were made by highly skilled craftsmen, spinners and weavers and croppers, often in their own homes. Well, the advent of the Industrial Revolution saw the introduction of new machines to do it in a very semi-skilled way, spinning frames, looms and weaving frames. Now, that just wasn't going to affect the world a little bit. That was going to be the end of these skilled craftsmen's trade. Their livelihood was gone. Now, a number of these people in Yorkshire didn't fancy that very much, and they got organised. And they got themselves into groups, and they progressively went around all of these new mills, and they smashed these machines that were going to change their livelihood. And that movement fairly quickly spread up to the northeast of England and down to the Midlands, in what became known as the Luddite Rebellion. But things didn't end very well for our Yorkshire Luddites. In 1812, a group of them, a local group of them, ambushed and shot and killed a local mill owner in a place called Crossland Moor, which is about 2 miles from where you're sitting down that way. And they immediately went into hiding. But they were betrayed. They were tricked into meeting in the yard of a local pub just down the end of Leeds Road here in a place called Cooper Bridge, where they were immediately surrounded by the militia. They were arrested and taken off to York and summarily tried. And in January 1813, 17 of them were hanged in York, and 6 others were transported to a place called Van Diemen's Land, which today is known as Tasmania. Used to send a lot of our criminals to Australia, and some of them have done pretty well. But that's a sad story. I haven't got time for a quiz, but I'm going to give you some numbers here to set our sector in context, really. You might guess ahead of me here. These numbers, there's a number there that represents the number of garments made annually around the world. It's 80 billion. In each year, 80 billion garments. 2 billion of those garments are pairs of blue jeans. And it takes 7,000 litres of water to make 1 pair of blue jeans. In fact, it takes 2,700 litres of water to make a t-shirt. And in the transition from a raw material to that t-shirt, the people doing it can choose from over 8,000 synthetic chemicals that are used for every aspect of that journey from raw material to finished garment. So we make a lot of clothes. We use a lot of water, a lot of chemicals to make those clothes. Where does it all go? Well, you know where it goes down the drain. So maybe no surprise that a number of commentators believe that 20% of all the world's water pollution comes from the fashion and textile sector, which is a bit worrying. So we make a lot of clothes, but boy, we buy a lot of clothes. In the year 2000, the average European bought 34 garments. By 2010, apparently, that had risen to nearly double, to 67 garments. A lot of statistics. What I really wish I had was the gender breakdown of that one. I can see some men in the audience saying 67 garments, that's too much. I see some women saying, is that all? But we buy an awful lot of garments and we throw a lot away. Typically, in fact, last year, your average European threw away 32 kilograms of clothing. And where does that go? Well, 85% of it goes into landfill. And perhaps most surprising statistic I found out of all, 10% of all the clothes made in the world never get sold, never get worn, they go straight into landfill. Now, I think there's some surprising figures there for all this clothing and all this material. But of course, it's not just clothing that we use textiles for. Furnishing, bedding, automotive, aerospace. And a lot of the treatments for those that people require, that customers need and legislation needs, is waterproofing and fireproofing. They also happen to be tremendously resource intensive in terms of water and chemicals. Just look at a couple of them here. Waterproofing uses a lot of chemicals, things like polysiloxanes and waxes, but it also uses fluorocarbons. We don't hear so much about fluorocarbons these days, but chlorofluorocarbons, CFCs, are all the rage, weren't they? 10 years ago when people were talking about holes in the ozone layer, they're still there. And they work best, so they're used most. They're activated or applied by padding on wet fabric after it's been heated up, and then pretty much they're baked on. It's a coating that's baked on in a process called curing. It's very high temperature, very energy intensive. And they do have a bad environmental impact, an adverse impact in terms of fluorocarbon in the atmosphere, basically because they're what's called bioaccumulative. They don't dissipate. They stay in the earth, they stay in plants, and they stay in you and me. Fireproofing doesn't look much better. Halogenated flame retardants include things like bromine, chlorine, iodine, and fluorine. Now, the brominated flame retardants have actually been banned in some states in America. In the EU, we have pretty tough controls on their use. But you all know as well as I do the proportion of clothing that's made in other parts of the world, particularly in the Far East, and their environmental legislation is way behind ours. They use an awful lot of these things. And there's some inorganic flame retardants as well, things like phosphates and phosphorus. So we produce a huge amount of fabric, and we layer and we coat and we laminate it with all sorts of different things. We're actually putting those chemicals on some substrates, some fabrics that have got a pretty interesting chemistry themselves. So that's the kind of breakthrough idea. We coat it and we treat it in these big, long machines, meters and meters long, that boil water, that use air to dry things. They use a lot of water baths and chemical baths. And so it works, but it's quite costly. Actually coating something with a good chemistry with even more. So the kind of breakthrough idea, the breakthrough moment is, well, hang on. Why don't we look at the chemistry of the fabric itself, the fiber itself, the raw material itself? Maybe, if we could alter it a bit, it might do the job that we're looking for. Wool is pretty naturally hydrophobic. So maybe if we can change the molecular structure of that substrate, we may not need to coat it in so many chemicals. So we know wool here, so let's have a look at what is wool made of. 33% of it, a third, is made of something called keratin. You're all very familiar with keratin. Your hair, your nails are pretty much made up of keratin. I think it originates from the Greek, the word for horn, which is kind of hair. 28% of it, this is raw wool, is grease. 12% is something called swint, which is the polite name for sheep perspiration. Then a lot of impurities and some water, but the interesting bit is this keratin. So what's that made of? Well, lo and behold, 50% of keratin is carbon. And carbon is what we're talking about largely to affect these changes. And some fascinating elements, great if you're looking to change the molecular structure of something, things like hydrogen, oxygen, nitrogen, and sulfur. So if you can take those elements, those raw materials, and change the way they operate, you could have a game on here, and you can. I haven't got time to go into the science of this, but you can see a machine here, and some of you will see the latest one this afternoon. Take it from me that if you bring together all sorts of energies in a gaseous environment where you've got a substrate and you know the makeup of that chemistry, like you're baking a cake, you can affect changes in the molecular structure of that fabric, that fiber, that can do anything for you. Naturally waterproofing, permanently fire retardant, and pretty much whatever you want. The science is basically 2 electrodes, ionized gas, like in a fluorescent gas tube, but super activated by pulsing high-powered lasers into it. Some of you don't believe me, I can see from your faces. We believed in it, and we developed a prototype system here 4 or 5 years ago, and it's down the corridor there. Not the best picture in the world, but that's the outside. This is what happens on the inside. Looking through a little perspex window down the length of this cabinet, you can see the atmospheric plasma, energized gas that's actually 2 meters long. When we pulse the laser into it 10 times a second, it glows. When we pulse it in 100 times a second, this is what happens. The whole of the inside of that cabinet becomes a reactor. It makes free radicals fly off. It puts much of the chemistry of that substrate actually into that cabinet, and it reforms in a different way. It feels the same, it looks the same, but it's different. So, if I can get it to move. We had some great expectations from this technology. We thought, well, hang on, this is taking a wet process and making it dry. This is, instead of using the energy of a massive long production line, using the energy of an average oven. This is taking away these chemistry and using the chemistry of the substrate itself. And you can see the scale of the ambition that we had. On the right side of the equation, all these tons of water, all these tons of chemicals, they're gone. There is no waste from this system apart from warm air. But there were the ambitions we had of this system. After 2 or 3 years of trials, we had an impartial environmental consultants come and compare this treatment, waterproofing, with traditional treatments of waterproofing, and the results were better than we thought. This system reduces the energy consumption by 99.6%. And you can see there was some pre-treatment of this fabric with some water-based things, so the water saving was only 75%. But you can see the chemicals and the exhausts were well down, and in terms of using the bioaccumulative chemicals, totally eradicated. This is the greenest, cleanest technology that you can imagine. And it works. The hydrophobicity, the fire retardancy has to meet international standards. Of course it does. If it doesn't do that, it's interesting. But we seriously and very consciously thought we don't want to do this in a laboratory in a university with a mini machine, because that would be interesting. We decided we're going to do it full scale, full speed, full width, and then the industry can really understand it. It can do a lot of things. You can see them up here. Not just waterproofing, fire retardancy. It can change the surface of material so it will print better and more consistently. And of course, an important thing, this isn't just in Yorkshire. Here in Yorkshire, people say he's got short arms and deep pockets, but every manufacturer around the world understands the importance of an economically viable prospect. This is a tremendously cost-effective system, hugely friendly to the environment, but it's consistent, and it's robust, and it's very simple to use. And we think that should make everybody happy, maybe apart from people who produce chemicals, but everyone apart from that should be pretty happy. Now, you might think that this is a laboratory experiment, that it looks a bit clunky. I'm going to show you a short video, which is actually the latest machine that some of you can see this afternoon, that runs at 55 meters a minute. So let's do that.
Unique, innovative, British. MTIX has developed the MLSE process to address the economic and environmental challenges of today's textile industry. The system synthesizes changes to the structure of fabrics to impart a diverse range of performance characteristics, from water repellency, fire retardancy, antimicrobial and improved dyeability, all at 55 meters per minute. Integrating multiple system elements and providing a simple operator interface, MTIX has developed a control system which allows full access to the individual components, providing a reliable recipe and batch processing schedule and performance reporting for batch traceability. Bringing together the plasma and laser energies in a controlled environment and a unique configuration provides the MLSE system with its patented technology. Using state-of-the-art handling systems, the MLSE equipment can be used to process the full spectrum of natural and synthetic material substrates at widths up to 2 meters. The cleverly designed system allows fabric to be taken off and then presented on rolls, trolleys or horses. The 4 processing zones allow multiple syntheses to be effected into the fabric on a single pass. Providing the continual supply for the different environments of the MLSE process zones involves a sophisticated gas feed system. Nitrogen generation minimises processing costs and minimises gas bottle handling. And a bank of chillers keep the system components within defined process parameters. All the discharge from the system is gaseous, which is passed through a catalytic filter before being exhausted cleanly to atmosphere. MTIX has invented the MLSE technology and has brought it to a production reality, offering industry a real alternative to traditional processing. The MLSE process provides a vehicle to revolutionise the textile industry. The patented technology can be applied to a wide range of textile processes, as well as offering the potential for technological advances in other industrial sectors. Unique, innovative, British.
Ladies and gentlemen, welcome to the next industrial revolution. Thank you.